Okay, yeah, thanks a lot, Sanjang. I work in an area called security. This means that besides crypto, I also get to build systems, and I work on programming languages. Our programming language group at University of Maryland is called PLUM, PL, University of Maryland. So I work with the plumbers, and this is a little lambda. Okay, so by the way, I am joining Cornell in the fall. Okay. So the plan is I'm going to talk about Oblivious RAM in the classical setting, and then Daniel Wicks will talk about ORAM with server-side computation, including onion ORAM, gobbled RAM, and reusable gobbled RAM. Okay. To begin with, I'll first talk about the problem of access pattern leakage that ORAM is trying to address. And I'll talk about the different manifestations of this problem in different application scenarios. Okay. The first scenario, consider you have a secure processor. And the secure processor, your cloud server, you have secret genomic data on your cloud server, and then to protect your genomic server, to protect your genomic data, you rely on the secure processor to encrypt your memory contents. Okay, but the problem is that even though your memory contents can be encrypted, if your adversary can observe this communication link between the secure processor and the memory, the attacker can still learn a lot of information. For instance, if the attacker observes that the processor is accessing locations related to the kidney problem, then he can infer that maybe this user is being treated for kidney problems. So that's very sensitive medical information. And in the real world, how do you launch this attack? This attack can be launched in various ways. For instance, if this attacker, let's say, is a system admin or an intruder to the cloud's data center, then he can launch physical attacks. He can probe memory buses to learn the memory addresses that are transmitted on the memory buses. But this adversary can also be a software adversary. So imagine the secure processor, I will talk about the SGX scenario later, where the secure processor relies on an untrusted operating system to serve page faults. And in this case, this untrusted operating system is going to be your adversary. Okay. So like I said, in this case, basically access patterns to even encrypted data can leak very sensitive information. Okay, a different scenario, and it's the same picture, but now instead of memory, we have this vertical cloud, and then we have the client. Okay, and the client is storing data in the cloud, and it's accessing the data. In this case, your adversary can be a network intermediary, like routers in the network, or maybe just, let's say, just the untrusted operating system on the client side, which is going to basically service these network requests. Okay. And there are some other settings where the problem is the same in nature, access pattern leakage problem, although at first sight, you may not immediately realize it. So Intel is going to, for instance, soon release this new SGX technology. SGX is going to be a secure processor that can encrypt memory. So suppose our favorite cloud provider, Amazon EC2, is going to offer SGX as a service. So secure compute as a service. And SGX hosts the server farm. We have many SGX servers running. And let's say they run a MapReduce task. Okay. So what's going to happen is that these SGX nodes are going to communicate with each other. You can think of this as like a distributed memory system, because the data is going to be split across these multiple servers. And by observing these access patterns, you can leak sensitive information. So for instance, specifically in SGX, you have the mapper and the reducer. Let's say the mapper, produces key value pairs, and key value pairs with the same key are going to be routed to the same reducer. So sometimes by observing, let's say, how many key value pairs are routed to the same reducer, you can gain sensitive information about the underlying data. Okay, so this is an ORAM problem in disguise. And similarly, oh, by the way, speaking of SGX, let me take a slightly deeper dive to look at what the adversarial model is. So in SGX, the sensitive application is going to run inside this SGX enclave. And this enclave itself cannot call OS system calls. So for instance, if this enclave needs to perform page swaps, then it needs to send a request to this untrusted operating system, and this operating system is going to serve these page faults on behalf of the enclave. And similarly for network requests as well. Like suppose this in this picture, these SGX enclaves are going to talk to other SGX enclaves in the network, and then these network requests are also going to be serviced by the untrusted operating system. Okay, so in this case, this is a software adversary. The untrusted operating system can basically observe these addresses, be it addresses of page swaps or addresses of network requests. Okay. So here is also a similar issue, but the context, replace SGX with secure computation. So imagine you have these servers, but instead of having SGX, you are relying on secure multi-party computation to perform privacy-preserving computation. And similarly, you can consider the memory as being distributed across these nodes. And then the communication pattern here would also similarly leak information. So this is the model that actually Elaine, Kaimi, and Raphael considered. They call it an Oblivious parallel RAM, and then they also used it to design large-scale secure computation protocols. Okay. So here's some ways to think about access pattern leakage. The first perspective is from a programming language perspective. Why do access patterns leak information? Because when we run programs on sensitive data, these programs can have control branches that depend on secret data. In this case, if the secret variable is 1, you read location X, otherwise you read location Y. And think about the secret variable as being the last bit of your secret key. So this is a bit abstract, and a more concrete example, for instance, is binary search. This is something that everyone is familiar with. When we do binary search, we are going to look in the middle, and depending on the result of the comparison, we either look left or look right. So if you simply observe the sequence of access patterns incurred, you can pretty much infer whether you are searching for a small value or a big value. Okay, and another perspective to understand access pattern leakage is from a statistical perspective. So, when we teach undergrad security, we tell the students deterministic encryption is not secure because of a statistical attack. And here the reason is similar. Essentially, the attacker can observe the frequency of the accesses and the co-occurrence, like memory location X tends to be co-accessed together with memory location Y. Okay, so in fact, a group of researchers from UT Dallas, they actually performed an attack on the an Enron email data set. So suppose this data is stored on the server in encrypted format, and there's a client making queries to the data. So both the queries and the data are encrypted, and all the server observes is the access patterns. And then they show just by observing the access patterns, you can infer like up to 80% of the search queries. And this attack leverages background information on the natural language corpus. Okay. So one thing to point out, people often ask me, is this a side channel? In many models, this is not just a side channel. Like for instance, in secure multi-party computation, the security definition of MPC basically requires that the access patterns be kept private. Okay, and also if you are a programming language person, it's also easy for me to explain why this is not a side channel. For instance, imagine this SGX scenario. Your application is actually, this SGX application is going to send these addresses to this untrusted operating system. And from an information flow perspective, these addresses are going to be tainted bits. So even if you just use the standard information flow type system, if your program leaks information through access patterns, it's not going to type check under a standard information flow type system. Okay. So how can we secure against access pattern leakage? We have Oded and Rafi smiling at us. We need Oblivious RAM. Okay, this was proposed back in the 1980s by these two people. Okay, so Oblivious RAM is a cryptography protocol that allows us to hide access patterns to data, and not only so, it also hides access patterns in a provably secure manner. Okay, and then since the seminal work by Rafi and Oded, there have been a sequence of subsequent works that improve on their results. So I'm going to talk about how to construct ORAM. And before I do that, I want to get some key intuition across. So one key observation is that in any ORAM scheme, the data blocks have to keep moving around. And why is this the case? So imagine if the data blocks always resided in the same place. What can happen? Okay, so suppose the CPU makes two subsequent accesses to the same location. And if this data block didn't move between these two accesses, then the adversary can observe that there's a linkability because it observes that the same block has now been visited twice. So this leaks frequency and co-occurrence information, and this is the kind of statistical attack that I was referring to earlier. So the key thing to keep in mind is essentially every time you read the block must immediately relocate. And if it doesn't relocate, like I said, the next time you read it, it's going to leak statistical information. Okay, so in the initial ORAM scheme that Oded and Rafi proposed, and it's called a hierarchical ORAM framework, and this is roughly what the scheme looks like. I won't have time to explain the construction, but the construction is very clever, and then they achieve, roughly speaking, log cubed overhead. And this means that in order for you to access one block, you have to pay, roughly speaking, log cube accesses on average to completely hide your access patterns. So in fact, actually, one of these log-n's, it's just a minor note, one of these log-n's is a security parameter. Basically, log cube n gets you an inverse Pauli failure probability. Correct me if I'm wrong, Rafi. And if you want to get a negligible failure probability, there's an extra little omega 1 there. But like in most of the talk, I'm going to just pretend we are happy with inverse Pauli failure probability to make things easier. Okay. So instead, I will talk about the tree-based ORAMs. Okay, so for tree-based ORAMs, you are going to see a tree. And the most frequently asked question by far is why is the tree upside down? When we were designing these ORAM schemes, we were considering the storage outsourcing scenario where there's the client and the cloud, and typically the client and the cloud is in the sky, and then the client is writing into the root bucket. So that's why the tree is upside down. Alternatively, you can also draw it in the soil. But then your cloud will be on the ground, and then everything will be pretty much upside down.
Aren't trees growing up?
Okay, but so I'm going to stick to this convention, and if you're uncomfortable, just tilt your head for the rest of the talk. Okay, so in the binary tree ORAM, I'm going to first talk about the initial binary tree construction, and then I'll talk about how to improve this to Pathogram and circuit ORAM, and then at the end of the talk, I'll also survey some of the more recent results. Okay, so every node in the tree is called a bucket, and the bucket has finite capacity. It means the bucket can hold a finite number of blocks. Some of these blocks are real blocks, and other blocks are dummy blocks. Okay. And here's the most important invariant of the scheme. Every block is assigned to a path. And when I talk about a path, it always means a path from the root to some leaf bucket. So here the block X is assigned to the purple path. In the beginning, I'm going to cheat a little bit. I'm going to pretend that the CPU is going to store a large position map that records where every block is. Okay. So given a data structure like this, reading a block is very simple, because in order for me to read block X, all I have to do is to look up the position map, find out that block X is on the purple path, and then I read the purple path. And I'm guaranteed to be able to find block X.
So you're not committing where X will be on the path. It's like one of those nodes.
Uh-huh.
It's not stored. It's just.
It's any X can be anywhere on the path. Okay. So the more tricky part is after I read block X, what do I do? Like I said earlier, every time you read a block, it has to immediately relocate. Otherwise, the scheme would not be secure. Okay, so now our job is to relocate X. And so basically, X can no longer be residing on the purple path. Let us now pick a fresh new path, namely the orange path, and let's try to assign block X to the orange path. Okay, so obviously we have to update the position map to reflect this, this change. What else do we have to do? Obviously, we have to write block X to the orange path. And how do we do this? Unfortunately, it's not okay to write X to the leaf node or any of the internal nodes. For instance, if you write X to the leaf node, then the adversary can observe that some block from the purple path is now relocated to the orange path. So the adversary can remember this linkability. Okay, and similarly, you shouldn't be writing to any of the internal nodes. And therefore, the challenge is how you can write the block back without revealing which new path it is. And there's a way to do this, obviously, and basically to write the block into the root bucket. The root bucket is on every path, so it's always unsafe to write the block into the root bucket. Okay, so at this point, so obviously if I keep doing this, then the root bucket will overflow, but disregarding this overflow fact, let's think about why the scheme preserves obliviousness. Okay, so what happens whenever you access a block, right? Observe that whenever you access a block, you are going to access a complete random path. And the choice of the randomness has not been revealed to the adversary earlier. So in this sense, the oblivious proof is trivial. Okay, so the remaining problems that I need to solve is, number one, how to deal with overflows. Like I said, this is bucket overflows, not buffer overflows. If you call each bucket a buffer, then you can call it a buffer overflow problem. And then we also need to see how to get rid of the position map, like I said in the beginning. And finally, I'll talk about some further optimizations that we can do. So how do we deal with overflows? The problem is that each bucket has finite capacity, and you cannot keep writing things into the root bucket, and similarly for every other bucket as well. So how can we prevent overflow of buckets for every bucket in the tree? And the idea is that we want to introduce this eviction procedure. Okay, and the goal of the eviction is to gradually percolate the blocks up the tree towards the leaves, and such that none of the buckets will ever overflow except with negligible probability. So there are conflicting goals for designing the eviction algorithm. The eviction has to happen slowly enough such that the cost is low. So for now, you can think of eviction as happening in the background, but the cost is charged to each access. And then the eviction has to be fast enough such that we can prevent overflow. I'm going to talk about a very simple algorithm for performing eviction, and it's called the random eviction strategy. And the idea is that every time you perform a data access, you are going to pick two random buckets at every level in the tree, and you perform eviction on these two random buckets. So what does it mean to pick a bucket for eviction? So suppose, let's say I pick this bucket for eviction. What I'm going to do is I'm going to pop a block from this bucket, and I'm going to write it to one of the children. But the way the scheme works, remember that there's this invariant. So when I pop a block, the block can only go one direction in order not to violate the main invariant. Okay, so let's say this block is assigned to this subtree, and then basically the block should go right. But in this case, in order to hide information from the adversary, we also need to make a dummy eviction on the left-hand side, just basically to put up the appearance that we are also making eviction on the left-hand side. Okay. So just keep in mind that every block is encrypted, and when the client reads the block, it will decrypt the block and re-encrypt it and write it back. Okay, so if you are going to overwrite the block, the new ciphertext has randomness, so basically the adversary cannot see which block has been changed.
Question? Here. You did this re-encryption on eviction or only on read?
On read as well, because read, you will need to remove the block from the bucket, which means encrypting a dummy block.
So you also re-encrypt every time you evict. Is that what you're saying?
But there are some, if you actually implement it on a secure processor, there are some optimizations you can do, like you can have a valid bit. So for instance, reading will just involve invalidating that bit. So you don't have to basically do re-encryption on the entire block. So these will save you constant factors, but if you don't care about constant factors, just imagine everything will be encrypted, re-encrypted as you write it back.
So then just to check, so you are like reading something, you move along the path, and somehow you decide that this guy has to be evicted. But this is a real thing. You cannot evict him randomly. You have to evict him along his path, right? So you have to put him on the right path. But you're saying you will make two writes, but the real one will be along the right path?
Yes. So basically, first I'm going to read back every block in this bucket, and some of them are real, some of them are dummy. And I pick any real block. It doesn't matter which one I pick, and I check to see whether this block should go left or go right. In this case, it should go right. So for the left-hand side, I'm just going to read back everything and write it back as is. But for the right-hand side, I'm going to read a block, see if it is empty slot. If so, I'm going to write this evicted block. Otherwise, I write the block back.
And you're saying you do it only for 2 nodes, or you do also for 2 nodes in every bucket?
So with every eviction, pick 2 random buckets at every level. So do it for 2 buckets at every level.
It's not correlated with the read path. It's just
not correlated with read path. This is the original binary tree scheme. Okay.
But you always evict from the root.
Yeah. Yeah, you always evict from the root. Okay. Yeah, the root is in some sense just a singular point. The root and the client stash are like more or less the same thing. Okay. So why does this eviction algorithm work? Actually, with not too much work, we can show that if the bucket size is log n, roughly speaking, and then none of the buckets will overflow with high probability. So actually here, high probability means inverse poly. If you want to get negligible failure probability, you need another little omega 1 there in the log n. Okay, so the idea is actually very simple. Why is it log n? And the intuition is very simple. I'm not going to do the formal proof. The formal proof is going to take a little more effort. And the idea is we can think of each bucket as a queue, and we just want the dequeue rate to be like constant factor larger than the enqueue rate. Okay, so what is the enqueue rate at level I of the tree? And it's not hard to see that it's 1 over 2 to the I. Because essentially at every time step, 1 block is going to come in. And if your queue is like stable, like if your queue doesn't grow unbounded, then essentially the rating has to be equal to the rate out, right? So essentially there's a rate of 1 coming in here, and then it's split into a half here and a half here, and it gets further split into 1/4. So therefore the rate, the enqueue rate is 1 over 2 to the I at level I of the tree. and the dequeue rate is 2 over 2 to the I because I pick 2 random buckets at every level to evict. So therefore, this kind of, informally speaking, this kind of behaves like a very standard MM1 queue. And this is what we learned in our undergrad probability class. And we learned that the queue length and the probability that the queue length exceeds R is proportional to something like 2 to the minus R. So falls off exponentially with respect to R. Okay, so that of course is not a formal proof because actually these queues are dependent. It's not a single queue. If it's a single MM1 queue, then it would have been the end of the proof. But it's a little more tricky because these queues are dependent. So in order to do the proof formally, you would either have to use the discrete version of the Burke's theorem, which allows you to derive an exact distribution on the queue length, or you can use a Chernoff bound if you don't care about deriving an exact distribution of the queue length. Okay. Any questions?
Would it help you to increase the degree of the tree?
Huh?
To increase the degree of the tree, would it help?
It wouldn't help reduce. It wouldn't help in an asymptotic sense. I tried the different things, and there's one interesting point, which is this flat partitioning scheme, where you only have, let's say, one level. It's basically flatten the tree into one level, but you have like square root n partitions with square root and each partition of square root n size. So that will give you a scheme where the client-side storage is like square root n. And then for each partition, you can kind of imply an ORAM scheme for each partition. So we actually, in our recent work on this network Oblivious RAM model, we consider a model where like each memory bank, the obliviousness within each memory bank is free. And you can only observe which bank the adversary is accessing. So in that paper, we use this flat partitioning technique. Okay, so I haven't talked about how to get rid of position map yet, but the idea is very simple. Instead of storing the position map on the client side, I'm going to recurse and store the position map on the server side in a smaller ORAM, and I will keep on recursing until I have a constant position map. Okay, so there are some tricks in parameterizing the recursion, and that's why these papers like have this dependence on the block size. So suppose your block size is like C log n, which is I guess what all these ORAM papers assume, and then you will have log n depth of recursion. Essentially, every level of recursion, you reduce the ORAM size by a constant factor, and after log n levels, you get constant size position map. So in this case, this recursion will incur an extra log n factor in the asymptotical bound. Okay, but there are other ways to parameterize the recursion. So suppose your data block is log n, roughly speaking, log n squared in size. And so you use, this is called the big block, little block trick. In this topmost level of the recursion, you are going to use the real data block size, which is log n squared. But then for these metadata levels, you use a different block size, which is log n. So you are still going to have log n levels of recursion, but all the metadata levels will only incur in total log n squared cost. So I need to be a little careful about what I say. So let's say each tree in the binary tree ORAM case, each tree itself will incur log n squared cost, because in order to read a path, in order to read a block, I have to read a path, and every bucket is log n in size, and then the height of the tree is log n. So therefore, within each level of recursion, the cost is log n squared. Okay, so in this case, if you do this little block, big block trick, then over all these recursion levels, in total you incur log cube costs because there are log n levels. And let's say in each level you incur log n squared cost. But even though it is log cube, because your block size is log n squared, maybe I should write this down. So for the binary tree, I'll pick it up. So say your block size is D, and in the top level you incur like D times log n squared costs, and then so this is the data level, and then for all the metadata levels added together, you will incur D times log n cube. So there is no more D, sorry. There is no more D here. So for the metadata levels, you use a log n block size. So you will incur this much cost in total. So suppose D is, in this case, log n squared. So as you can see, basically, in order for me to read a block of D in size, I have to in total read, roughly speaking, log to the 4th bits. So therefore, the bandwidth blow up is roughly speaking log n squared. And therefore, in this case, the recursion doesn't incur extra asymptotic overhead. Okay, and another interesting point is that when the data block is very big, and you use the same block size for both the metadata block and the data block. So if your block is n to the epsilon in size, then you have constant levels of recursion, and therefore the recursion also doesn't incur extra asymptotical costs. Okay, so this is just the basic idea for the binary tree scheme. We can improve the eviction algorithms to reduce the bucket size to constant. Like in binary tree ORAM, the bucket size is log n. So how can we reduce this to constant? So I'm going to very briefly talk about Pathogram and circuit ORAM. Okay, so in particular, circuit ORAM can actually achieve, roughly speaking, log n cost, log n bandwidth blowup with constant CPU cache. And this holds for log n squared block sizes. And this actually matches the Gorik-Ostrovsky lower bound. The lower bound specifically actually, so essentially Gorik-Ostrovsky, they show a lower bound that any ORAM scheme with constant CPU cache must incur at least log n costs. Okay, and then the lower bound holds regardless of the block size. So this matches the lower bound for, like, roughly speaking, log n block sizes, or log n squared block sizes. And then for smaller block sizes, we don't have a matching upper bound. Okay, so Pathogram, this is due to Emil Stefanov, Martin van Dijk, and others, the SCFRYD part. And so Pathogram and the improved variants have been implemented in 2 secure processor prototypes, the Ascend processor and the Ghostwriter processor. So Ascend is built by this team at MIT, including Srini Davidis, Chris Fletcher, Ling Ren, and others. And actually for Ascend, they actually sent their processor design to a factory to be fabricated for real. So this is going to be exciting. Okay, Pathogram algorithm is very simple. In order for me to access a block X, I have 3 steps, right? It's like, have you heard of the how to put an elephant in a fridge? There are 3 steps. Open the door, put the elephant in, and close the door. So here we have 3 steps too. Number 1, you look up the path, and of block X, and it is, let's call this path P. And number 2, you read the path P into your stash. And number 3, you try to write the stash back to the same path. And what is key here is you try to pack these blocks as close to the leaf as possible. And this has to respect the invariant. Remember, not every block can go into the leaf, depending on where the block is assigned. So if you have a tree like this, and let's say this is my path, and I have my stash on the client side. So if a block is, let's say, assigned to this subtree, then this block cannot go beyond this point on this path. The furthest the block can go is here. Okay, so based on this invariant, I'm going to try to pack the stuff that's in my stash as close to the leaf as possible, and I write back as many blocks as possible. And everything I fail to write back still remain in the stash.
So will you show an example, or that's all you're going to say, or you will expand on this?
I can talk a little bit about the proof intuition, but is the algorithm clear? No. It's not clear? Oh, okay. So
just use an example. What's the example contents of the stash, and what happens to it when you have path P?
That thing is an example, no? When there's the block there, it wants to go to the blue triangle, it goes down the path, and at some point it splits off of the blue triangle.
So
there's more than one block there, right?
Oh, every block.
Every block.
You try to push everything.
Yeah.
so let's say you have a path. Okay, so this corresponds to this path I draw here. And for simplicity, let's assume the bucket size is 1. Okay, and I have some block in my stash. Let's say there's just a single block in my stash. And imagine this block is assigned somewhere in this subtree. So let's say that this block is assigned to this leaf. Okay, so I'm going to compute the least common ancestor of this path and the current read path, which is this point. Okay, so in order to write this block back, I'm going to try to, let's say this corresponds to this level. So I will first try to see if this level is 4. If this level is 4, it means I cannot write the block here. Okay, so this level is occupied, this level is occupied, and this level is occupied. So then I will try to write the block into this level, and it still fails. And then I try to write the block here, and this level is empty, so then the block gets written to this level. So it's basically, in some sense, it's the most aggressive eviction algorithm possible on a single path. And it is.
Usually you evict, previously you were evicting to the leaves, and here you try to evict towards the root. It's like the opposite.
So this is the leaf. Just to be clear, this is the leaf, this is the root. And I still, let's say this block can actually go into the leaf and the leaf is empty, then I will end up writing the block into the leaf. So which means, like remember in the binary tree algorithm, every time I just evict one little step, but here actually the block can immediately be evicted to the leaf. So you can basically evict many steps.
And what if everything is full?
And then stuff just remains in the stash. And then most of the work of the scheme is to basically bound the size of the stash. Okay, any other questions? Is the scheme clear now?
You said the stash is constant size?
And no, it actually, this is the next slide. Oh, this is in a couple more slides. So the algorithm is very simple, and you can write it in the 3-line fashion. You can also write it a little bit more formally. And this is the pseudocode in our paper. It's basically 16 lines of pseudocode, and this counts lines such as endif and end4. It's so simple you can print it on a T-shirt.
The measure is whether you can tweet it.
Good measure, right? Yeah. So you asked about the stash. How big is the stash? So we basically formally prove that the stash growth, the probability that the stash exceeds R is bounded by something like an e to the minus R. So how do you do the proof? I can talk about the intuition pretty quickly. Okay, so in order to do the proof, we are going to have an imaginary ORAM called the infinity ORAM. And in the infinity ORAM, every bucket is of infinite size. So infinity ORAM is actually not a secure ORAM scheme. It's just a construct that lives in the proof for bounding the stash. Okay, so now I'm going to run the same Pathogram algorithm, but on the infinity ORAM. And in the infinity ORAM, because every bucket has infinite capacity, a block is always, in this case, the least common ancestor is here. So the block is always going to be assigned to the least common ancestor. It's always going to be assigned to the place, the furthest possible location the block can go. In fact, it's not hard to relate the stash size in the real Pathogram to some characterizations of this infinity ORAM. Essentially, we show that if basically in the real ORAM, if your stash size is bounded by R, and that's equivalent to saying in the infinity ORAM, so we are going to consider every possible subtree rooted at the root. So the subtree can have weird shapes, like it can be like some tree like this. It can be a partial tree. It doesn't have to be a complete binary tree. So let's say this is the root. So this can be my subtree, and the subtree is basically part of the bigger tree. Okay. So essentially, if for every subtree, its usage is bounded by 4 times t is basically, this is the size of the tree. And then 4 is a constant that's related to the bucket size. So as long as the usage of every subtree is bounded by 4t plus r, then this equates to saying that the stash size in the real ORAM is bounded by r. If you think about it, it's actually quite intuitive because essentially you can think of Pathogram as always evicting things to the, forget about the block size, evicting things to the furthest location where it can go, and then you can do some kind of post-processing to pack things, repack things to satisfy the bucket size constraint. Okay. And then whatever overflows into the stash. Okay, so what's nice about this is now basically in order to do the proof, I only have to reason about this infinity ORAM, and this infinity ORAM is much easier to reason because I have this very nice property that whenever a block gets evicted, it will go to the place, the furthest place it can legitimately reside. So there is actually one version of Pathogram that's actually relatively easy to prove. How much time do I have?
15
minutes.
Well, why don't I finish the rest of the... do you want to listen to the proof or go?
1 second. I think it's longer.
No, it's the same length. Okay.
Should I try to do the proof, or should I go forward? And maybe if we have more time at the end, I can come back to the proof. So there's basically one version of Pathogram that's relatively easy to prove, and I can explain the intuition in like 10 minutes or something.
Okay.
Okay.
You can take 10 minutes from my talk, it's fine.
Huh?
You can take 10 minutes for my talk.
Yeah, that's what I wanted to say. The two of you together have 2 hours and 15, which is longer than 2 hours.
Okay.
As far as I know.
Okay, sure.
The concept.
So this version of Pathogram, the version of Pathogram that's simplest to prove actually will rely on an eviction technique that's introduced by Gentry and Mariana, maybe Shai, in the PATS 13 paper. It's called deterministic order eviction. And the idea is that in Pathogram, you evict on the read path. So you read the path and you evict on the same path, but you don't necessarily have to do that. You can pick other paths to evict as well. So in deterministic order eviction, the idea is that you are going to pick the paths in a deterministic order, and specifically you will pick in what's called reverse lexicographical order. And what this means is that you are going to write the index of the leaf node in binary format, base 2, and then you reverse these digits, and that determines the eviction order. So what happens in practice is like basically you are going to evict the leftmost path first, and then you are going to evict this path, because this is like 0, 0, 0, 0, let's say, and then this is 1, 0, 0, 0. And then the next one you evict will be, oh, I'm bad at counting, 0, 0, 1, 0.
Quarter one.
It's in the one quarter.
Okay, this one. And so on and so forth. So this eviction strategy has the very nice property, and that so essentially, I want to show that for every subtree T, the usage is going to be bounded by 4T plus R. But instead of, so what's going to happen is you are going to do a union bound all of the 4 to the, there's 4 to the n, roughly speaking, subtrees, and you are going to do a union bound on all of these subtrees. But instead of considering arbitrary subtrees, it's easier to consider subtrees that are regular. So that let's say I'm only going to consider subtrees that are flat. Okay, and I'll explain the intuition for these flat subtrees, and then you can kind of extend the proof for arbitrary subtrees. Okay, so this is going to be my subtree, and if your eviction order follows that deterministic order eviction, basically, let's say I evict this path. Okay, and the next time I come back to evicting this path will be exactly after, let's say this level has size 2 to the I. So after exactly 2 to the I steps, I will come back and then evict this path again. Okay, so now I ask the question, how many blocks are in the subtree? Okay, so let's consider every block as being assigned to one of these exit nodes at the boundary of the tree. And in order to, we can do an expectation analysis, and then it's not hard to show that basically the number of blocks in this subtree is like some constant times the size of the tree. And then if you know the expectation, in order to prove a high probability tail bound, you just have to do something like a Chernow bound. Okay. So how many blocks would remain that are assigned to one specific exit node in the subtree? In the infinity ORAM, every time I can come back to evict this path, and then basically everything will be evicted away from, because the buckets have infinite size. So every time I basically evict this path, then things will go out. But in between these two evictions, like 2 to the I time steps, 2 to the I time steps have passed. Okay, and in every time step, there's roughly speaking 1 over 2 to the I probability that something will be assigned to this specific exit node. So times something like 2 to the I. I'm omitting all the constants here. So basically you can show that every exit node has about constant number of blocks assigned to it. And then you sum up all of these exit nodes, you get something like that's basically constant times the size of the tree. So it's basically the expectation analysis is very simple, and then you just do a trade-off bound, and you can show this high probability tail bound. Yeah.
Why does it matter in which exact order? I understand the deterministic, but why does it have to be reversed lexicographic order? Why does the order matter?
And you can also do random eviction. It makes the proof a little harder.
Deterministic, but why this order?
You want this thing of coming back to the node every 2 to the I thing happen in every single subtree, and that's the only order that satisfies that.
Right. In this case, basically, after exactly 2 to the I steps, you come back to evicting the same path. And that's why you can do this very simple expectation analysis, because in every time step, there's this much probability that something will be assigned to this exit node, and then over 2 to the I steps, you get constant number of things assigned to this exit node. Okay. I guess from an intuitive perspective, because this path has the least overlap from this path, so if you want to be aggressive, you want to evict a path that has the least overlap with what has been previously evicted. Okay, so that's Pathogram. And Pathogram is great for implementing in secure processors. And if you want to implement ORAM in secure multi-party computation, things are a little different. So RAM model secure computation was first proposed by Ostrovsky and Shoup, and then Gordon et al. Implemented RAM model secure computation using the binary tree ORAM in 2012, and then this is the latest result on malicious secure RAM model computation, and it appeared in Eurocrypt 2015. Okay.
So then let me just understand. So there is this binary tree RAM, there is Pathogram and Circuitous RAM. And I understand the chronological order, but so my understanding is circuit is strictly better than path, strictly better than binary tree?
Circuit ORAM is asymptotically, from a theoretical perspective, circuit ORAM is strictly better than path ORAM, but from a practical perspective, if you want to implement in secure processors, path ORAM is a little better, because in path ORAM, you can afford to have the CPU store, let's say, a log n size stash. That's not very expensive, but by having this little stash, you can shave constant factors off the data axes.
But strictly, and path is strictly better than binary tree.
Yes.
Binary tree, and that is strictly better than original Rafi thing, right? Sorry, I just want to make sure.
Rafi scheme has log cube too. So basically, the binary tree ORAM, it's a little complicated. Basically, for log n square block size, it's better. For smaller block size, the asymptotics are the same. But for the original hierarchical ORAM, you have to apply this complex deamortization scheme to get a good worst case cost. Because if you just implement as is, sometimes you have to take the whole memory and reshuffle everything. So occasionally you are going to incur linear cost. But there's a very nice deamortization trick that you can use.
I see, but still, state of the art is a circuit RAM. So if you use at least from theoretical perspective circuit RAM, you don't need to know about other stuff, right?
To understand circuit ORAM.
Well, no, I mean, if you want to use it in, let's say, a theory paper or something, you just use circuit RAM. You don't need to know the other stuff. You need to know everything.
Again, it's a trying to optimize the citation.
Okay, so circuit ORAM, and let me explain why we were motivated to study circuit ORAM. So we implemented some of these ORAM schemes in secure computation, and it turns out that, this is the secure processor figure. So in the secure processor case, we can see that path ORAM gives you the best bandwidth blow up. But when we implemented this on top of MPC, we noticed that Pathogram is not even as performant as binary tree ORAM. And there's a reason why. Because if you think about the Pathoram's eviction algorithm, this is difficult to implement as a circuit. Like if you want to do MPC, everything has to be implemented in the circuit. And the Pathoram's eviction algorithm says you pack things as close to the leaf as possible. So the naive way to implement this is to do a double loop. Like I'm going to read one block in my stash, and I'm going to look over all possible positions on the path and evict that block. And then I'm going to grab another block from my stash, and I will look through the whole path and try to evict this next block. But this will incur like something like log n squared overhead to implement the eviction algorithm. And essentially the problem is that you have to make log n scans over this path, and you don't want to do that. And there is a way to make the Pathogram eviction algorithm oblivious using something like oblivious sorting. But actually, as we discovered the scheme, we tried the asymptotically better version of the Pathogram eviction implemented as a circuit. But actually, in most cases, it doesn't perform as well in practice as the naive Pathogram eviction implemented as a circuit. So this motivated us to look for a new algorithm.
In that graph, what's the y-axis? The graph that you showed.
This graph?
Yeah.
So Pathogram, basically, now we are in secure computation land, right? So everything has to be implemented as a circuit. So in Pathogram, if you want to evict the stash onto your path, you are going to, the naive way is to do a double loop. You say for every block in your stash, and then you look at every position on the path. For every position, let me call it, for every slot on the path P, and I'm going to try to every slot, let me call the slot S. So I'm going to try to write B to location S. So this is the naive way to implement Pathogram in a circuit. Remember, when you implement things in a circuit, you cannot make dynamic memory accesses anymore. So essentially, the algorithm has to be oblivious. Okay. So this algorithm will make log n scans over the path. And I don't want to make log n scans over the path. It's too expensive. Okay. So what we really want is to be able to evict in a single data scan over the path. Okay, so Pathogram requires log n data scans over the path. How can we do it in a single data scan? So let's just try. And I'm going to talk about a broken idea. Okay, so this is the root, and this is the leaf. Okay, and I will try to evict things upwards. An arrow here means, so all of these, okay, never mind. So basically an arrow here means that this red block can legitimately reside in level 2, but not beyond. Okay, so this basically is a result of the main invariant of the scheme. So now I'm going to make one scan over this path. And as I scan level 0, I'm going to pick up this red block. Okay, so if I'm greedy, I'm going to try to pick up a block that can be evicted the furthest. So pretend I'm going to be greedy and do that. Okay, so now I go to level 1. And I have to make a decision whether to drop this block inside this level. in this case, obviously, the best thing to do is not to drop the block in this level, because the red block can actually go to level 2. The right thing to do is to write the red block into level 2. Okay. So in this case, I happen to do the right thing. But in an alternative world, everything in the starting position is the same. The only difference is that in this case, level 2 is it's fully filled. Okay. In this alternative world, the right thing to do. Oh, what's going on? The right thing to do is to pick up the red block and then write it to level 1. So I should not have held on to this block when I scan level 1, because if I held on to this block, later I'm going to discover that there's no place for me to write this block anymore. So I end up holding this block, and then there's nothing I can do with it anymore. And the problem basically is lack of foresight. When I start the scan, I don't have any insight on when I should pick up a block and when I should write a block. So therefore, the idea is very simple. We are just going to do 2 metadata scans to develop the insight that's necessary to eventually do this data scan in one shot. So I'm not going to describe the algorithm in detail. I'm going to play this animation. Okay, to start with, basically these blue blocks are the ones that can be evicted further within the same level. Okay, so every level has 2 blocks, and in this case, this blue block can be evicted further than the black block. Okay, and in the first metadata scan, I'm going to develop these blue arrows, which is my metadata, and then in the second metadata scan pass, I'm going to develop these green arrows, and this green arrow essentially provides a recipe on what to do when I do the full data scan. So eventually, when I actually start doing the full data scan, I'm just going to follow the green arrows, and this provides a recipe on what to do. So essentially here, I pick up a block, and the green arrow says I should put it in level 1. So I do that, but I pick up another block from level 1, and then according to the green arrow, I should put it in level 3. So I do that, but I pick up a block in level 3 at the same time, and then this goes on. So then I complete the full data scan. Yes?
What if you just tried to do a randomized thing, and at every level you flip a coin? If it's heads, you place it. If it's tails, you carry it.
I don't think the stash will be bounded. That's just I'm not sure if we tried many different things. We basically tried maybe like 20 or 30 different schemes, and initially a variant of this worked, but we couldn't prove it, and then we modified the scheme.
Purely randomized without any metadata.
My gut feeling is that the stash won't be bounded, because the thing is actually pretty tricky to make it work. We try lots of different things. Like I'm sure we try ideas like this one. Yeah.
Just to make sure that you're not actually implementing the most aggressive eviction from the Pathogram. This is a different eviction strategy. It would not necessarily push everything as far as it can go.
Right. So this is a milder eviction. It's not the same as Pathogram's eviction. But speaking of most aggressive, it is not the most aggressive eviction scheme over the path, but it is the most aggressive eviction restricted to a single data scan. So that's another way to think about it.
This is the theorem that you proved.
We didn't prove this, but if you think about it, that's the best thing. Because it's kind of like saying, had you looked at it in hindsight, what would you have done, right, to evict this? To formally show it, you have to define what is most aggressive. But if you really want to formalize this, you can.
And it's still constant size bucket?
Yeah. It's still constant size bucket, and the proof kind of follows the same overall framework as Pathogram, where we kind of prove things in this infinity ORAM world, except that in this case, proving equivalence to the infinity ORAM is a very, very complicated induction proof. Like in the case of simple inductive proof. In this case, actually, I didn't believe it was equivalent in the beginning, and I argued back and forth with my co-author Hubert, and he believed it was true, and in the end, we proved that it was true. It was very subtle, like.
So just to understand, in terms of eviction strategies, this is strictly less aggressive than Pathogram, but you're saving time by like shaving a log factor or something, right? So this is kind of, you hope it's faster, you hope to lose like maybe only a constant factor in terms of aggressiveness and gain log factor in terms of speed. That's the intuition?
So you have to be a little careful here. From an asymptotical perspective, Pathoram's eviction can be implemented with the log n circuit using oblivious sorting. But it's just that is in practice is not even as efficient as that double loop thing.
And here you can do it in what?
Basically a log n size circuit.
I see.
Because the metadata scan are constant number of metadata scans, but also another practical saving you get is that the metadata scan need not touch the real data blocks. So typically, if your data blocks are much bigger than your metadata, then you also get a constant factor there.
And the stash size is the same in both cases? It's like log n or something? Or?
Yes, the stash size, the asymptotical distribution is similar. Basically, the probability the stash exceeds R is proportional to like e to the minus R. Yes.
Is there any reason we want an aggressive eviction strategy except that it will enable bounding the stash size?
We want it to be, because like in the binary tree ORAM, the bucket sizes are log n, and that introduces another...
My question is, given two schemes that have the same bucket and stash size, one with an aggressive eviction strategy or a less aggressive eviction strategy, it doesn't matter, right?
It doesn't matter, but except that for Pathogram, it's good for the secure processor, but it's not very good for MPC type of benchmarks where you have to implement the eviction algorithm as a circuit, like not in the RAM model. Typically, when we think about algorithms, like we usually think of it in the RAM model, where you have a CPU accessing memory and you express your algorithm's complexity in the RAM model. That's what the algorithms community does. But in the MPC world, everything has to be expressed in circuit complexity. Okay.
5 minutes.
Okay, so I'm going to just quickly wrap up. When we implement circuit ORAM in circuits, it's roughly gives you like 50x smaller circuits than Pathogram. The break-even point with linear scan ORAM is very small, like basically 1 kilobytes, which means if your payload is 32 bits, like a 32-bit integer, if your array size is only 256 entries, you are better off using circuit ORAM in comparison with linear scan ORAM. Okay, so just I'm going to quickly talk about some of the recent results in this space. New models for Oblivious RAM. Elaine, Camille, and Raphael has Oblivious parallel RAM. And in this case, instead of having a single CPU, you have n CPUs. And then they're accessing the memory in parallel. So they have a very nice scheme that can do that. And then this can be, this is a building block that's used to design their large-scale secure computation paper. Okay, and then we also have a result on Oblivious network RAM, where within each memory bank, the adversary cannot observe the offset within each memory bank, but the adversary can observe which memory bank you go to. So this is this work shows some interesting connections to the parallel algorithms literature. Like we use some very nice known results from the parallel algorithms literature that gives you these log star n algorithms. So that's why our paper has log star n, which makes it cool. Okay, and then also related is Oblivious algorithms and parallel Oblivious algorithms. If you see a paper that's something like secure computation for task X, chances are this is an Oblivious algorithm paper. And these papers are these works are basically concerned about taking a specific task and express this as an Oblivious algorithm. So Oblivious algorithm and circuits are in some sense translatable. So if you want to implement anything on top of MPC, you have to express it as a circuit, which means you have to express it as an oblivious algorithm. Okay, so we have been developing programming language frameworks to make tasks like this easier. So essentially, a lot of cryptographic primitives rely on expressing programs as circuits, and in these cases, ORAM oblivious algorithms would be relevant. Okay, and then there are in the systems and programming language literature, people have worked on programming frameworks that help this program to circuit conversion, and this actually occurred in both the secure computation context and the verifiable computation context. There are similarities between these two lines of research, but they are also different in the sense that in MPC, you have to express the circuit the task you want to compute, whereas in verifiable computation, you express in circuit basically the program for checking that the computation is correct. So this checking that the computation is correct in some sense is a lot easier than expressing the computation itself in circuit. But nevertheless, like if you look at these works, like they also kind of rely on oblivious algorithms like oblivious sorting to do these and to express this as a circuit. Okay, so we have been building this framework, Oblivious RAM. I guess Chang is here. Are you here? No? And we basically help the non-specialist programmer, can write a program and then we compile it into an oblivious counterpart. And then our compiler actually has been integrated with both the ORAM-based secure processor and on top of a secure computation backend. So this is pretty cool. Like for instance, like 2 years ago, if you were to implement matrix factorization, design a customized oblivious algorithm for matrix factorization or ridge regression, this would have taken you months to accomplish. But with our framework, you can do the same task like in 1 day, and we achieve better performance. And actually, the framework, our framework provides programming abstractions. So if you write your program in our oblivious programming abstractions, we emit to oblivious algorithms that are competitive to the custom designs. And our programming framework can type check that our program indeed satisfies obliviousness. And what is more cool is that we had these programming abstractions and we are composing them to write new algorithms. And what was surprising to us is that by doing so, we happened to solve some open problems in oblivious algorithm design. We realized the thing we end up with is actually more efficient than any oblivious algorithm known previously.
So what's the simplest example of an oblivious algorithm? What do you mean?
So let's say you want to have a shortest path on sparse graphs. You can write this program very easily using our programming framework. And we offer several programming abstractions. One is called the loop coalescing abstraction. I mean, think about a programming abstraction as MapReduce. Right? MapReduce is a programming paradigm. So we offer several of these. Like one is oblivious data structure, and the other is loop coalescing. And if you were to implement shortest path in our framework, the easiest thing to do is you take one of these loop coalescing abstractions and you combine it with oblivious data structure. Like Dijkstra has this oblivious heap thing, right? And then we basically implement this thing, and then we realize actually the resulting algorithm is asymptotically more efficient for sparse graphs than previously known algorithms.
So you don't use like oblivious RAMs here. This is like dedicated oblivious algorithms for various tasks.
So our framework falls back to oblivious RAM. So we provide generality, but if you use any of our programming abstractions, we can do optimizations and emit oblivious algorithms instead of generic ORAM. So we kind of want to provide the best of both worlds, both the generality and the efficiency of customized algorithms.
So this RAM is secure processor. What does it do? Does it compute the same circuits and you would also compute it for secure computation, or?
The secure processor implements the ORAM controller on chip.
What is the ORAM controller?
ORAM controller is the ORAM algorithm. If you were to implement it on top of a secure processor, the ORAM algorithm has to be trusted, so it has to be implemented on chip. So basically, this programming framework, I can talk about it for another hour, but of course, I'm not going to do that. Thank you. A bunch of us are going to go boating in this park in Mountain View on Sunday. If you want to join us, please let me know. This was one of my favorite places in the Bay Area.
Is it going to be Oblivious boat?
So I'm sure Elaine will be happy to take questions.
Yes, I have a
Let's thank her again.